All right, so in today's video, I'd like to cover 11.10. And again, this is coming after these videos that you should have watched beforehand, right? These kind of pre-class videos. So make sure if you haven't watched these already, pause, go and watch those, and then come back and watch this video. But the first thing that I want to do, typically anyway, is to go over these pre-class videos and just kind of refresh ourselves what we should have taken away from them and what we're going to be building on for our video here. So in the pre-class video, we talked about Taylor and Maclaurin series. This is another way to generate power series. So again, we're going to be generating these infinite polynomials. And the idea with Taylor and Maclaurin series is that we're going to use the information about the derivative in order to come up with the coefficients for our polynomial, our infinite polynomial or power series. And so we talked about that quite a bit. And then we got this nice general formula. Again, if you want to know what your coefficient for the nth term is, it's going to be the nth derivative. So that's what this notation is right here. So first derivative, second derivative, third derivative, fourth derivative, all that sort of stuff. You could also represent these with some prime notations where you just do the little hash marks there. You're going to evaluate at your center, so whatever your center is, a in this case, and then you're going to divide by n factorial. And there's a nice proof of why this is the right coefficient to choose and how it kind of captures all of the information about the derivatives at this particular point, the center that we're kind of expanding around. Okay, we talked about, this is kind of the general formula for a Taylor series. If, however, your center is 0, this is what we call a Maclaurin series. So Maclaurin series is just a Taylor series, but you're centered around 0. So that's just a little bit of vocab that you have to have memorized. Other than that, not so bad. And then we go about actually utilizing this stuff, right? We actually find the second degree Maclaurin polynomial for a few things. We talk a little bit about remainders and whatnot, and I'm going to get into that considerably more in 11.11. It's kind of a bit vague, in the book they start to talk about the remainder here in 11.10, but they also do it in 11.11. And that's really where we're going to focus on, and that's where kind of you'll see the majority of this remainder stuff as far as web work homework goes is actually in the next bit, the section 11 stuff. So although we bring up the remainder and everything, here we're kind of, again, talking about just finding the Taylor series, centered at a equals 2 in this case for this function. And we do a few more examples like this. And we also get kind of the general rules here, this nice table of kind of for a lot of the functions out there, what do the power series look like, or what do the Maclaurin series look like? Notice that all of these are centered about 0, right? We just have x to the n, or you could say x minus 0 to the n, x minus 0 to the n. Again, just x here. You can see this one doesn't have any even terms, though. They happen to all be 0. This one doesn't happen to have any odd terms. This one doesn't happen to have any even terms. But again, they're all centered around 0. You don't see x minus 5 raised to the n power or anything like this. It's just x to various powers. And then we also bring up the last one here is these binomial coefficients and everything. And again, we'll kind of elaborate on this a little bit more, especially in section 11. So, okay. This is some useful stuff, and then we go about, we actually did a proof of why this works out. But that's kind of the videos in a nutshell. So that's kind of what I wanted to cover. Let's go ahead and transition and look at our new problems for today. So here we are, new problems for today. On the exam formula sheet, I wanted to bring this up really quick, that you're actually given these things, right? So these formulas are provided for us on the exam formula sheet. And so I'm going to kind of view 11.10 slightly differently than maybe I did in the pre-class video notes. And I think that really when you get kind of a general function and you want to create a Maclaurin series for it, or you want to create a Taylor series for it, there's kind of an order of operations that I would go in. And so here I'd like to give you that order of operations in order to how would I solve particular types of problems. So the first type of problem is that I would like to use this very nice information here in order to come up with some new series. So for instance, in example 1, like it mentions here, right, using these we can find many other Maclaurin series or Maclaurin polynomials. So I'd like to find the Maclaurin series in sigma notation for this function right here, x e to the x, and then we'll also state the radius of convergence for this new series. So again, remember these Maclaurin series, power series in general, Taylor series, right? These are infinite polynomials. And when I look at this, right, I'm completely happy with the x. The x is already a polynomial, but the thing that's not in polynomial or infinite polynomial form is this e to the x. But this is where we can come up and use this bit right up here, right? We know how to turn e to the x into some infinite polynomial. It's the sum from n equals 0 to infinity of x to the n divided by n factorial. And notice that the radius of convergence, it's good. No matter what x value you plug in, it has an infinite radius of convergence. So we're going to go ahead and we're going to do x times, and instead of e to the x, I'm going to do the sum from n equals 0 to infinity, x to the n divided by n factorial. And again, we want this in sigma notation, so I'm happy how we have it here. But again, let's go ahead and combine all of our x's and all of our coefficients. So I'm going to go ahead and rewrite this, summing up from n equals 0 to infinity. The stuff without the x's, well, that's going to be 1 over n factorial. So these are our coefficients. And then, let's see, we have x to the n, and then we have an extra x. Remember, we multiplied by this. So this is actually going to be x to the n plus 1. We have one more than we originally had. So this right here would be the power series, or the Maclaurin series in this case, representation for e to the x. And it asks to state the radius of convergence. Well, multiplying by x does not alter the radius of convergence. And so remember, for e to the x, the radius of convergence was infinity. So this will still have an infinite radius of convergence. All right, that's part A. Part B, another sort of trick here. We have sine in this case, sine of 3x squared. And kind of, again, we should think of this temporarily as sine of u or something like that. And remember, up here we have, from our formula sheet stuff, we have a way to represent sine as an infinite polynomial. And so the way that we represent sine as an infinite polynomial is going to be summing up from n equals 0 to infinity. We have this alternating piece, and then we have just the odd powers. So x to the 2n plus 1 divided by 2n plus 1 factorial. Oops, so I was using u for my variable, so this should really be u here. There we go. And in this case, my u is just 3x squared. So now we're going to go ahead and substitute in. Everywhere we see a u, we're going to put 3x squared. So this is going to be summing up from n equals 0 to infinity. And again, I really like to combine all my coefficient stuff together. So I'm going to write this as negative 1 to the n divided by 2n plus 1 factorial. And then the variable stuff, right, u, that's going to be my 3x squared raised to the 2n plus first power. And so I could go ahead and rewrite this one more time just to kind of simplify things a little bit. Summing up from n equals 0 to infinity, we're going to have negative 1 to the n. We're going to have still my 2n plus 1 factorial. But now there's this 3 here that's being raised to the 2n plus 1. That doesn't have any x's in it, that 3 itself. So I'm going to go ahead and combine this over here. We're going to have 3 raised to the 2n plus 1. And then for the x's, right, notice this is x squared, and we're raising that to the 2n plus 1. So remember, when you have powers raised to more powers, they multiply together. And so we're going to have x to the 4n plus 2. So that's just 2 times the 2n plus 1. So this right here would be my final answer. This is what it looks like in this sigma notation, or the summation notation. And again, remember that the radius of convergence for sine was infinity. So this will also be infinite. And kind of a little bit more formally, right, we had kind of a u here. So I would say that u should be less than infinity, right? So that's the radius of convergence statement that we got back from 11.8. And then we could go ahead and substitute in 3x squared. The absolute value of that should be less than infinity. And when you divide by 3 and when you take the square root, unfortunately that does not get you off infinity. So that's why the radius of convergence for x will also be infinity. All right, so this is how we can use this stuff in order to come up with these infinite polynomials, these Maclaurin series, but you could also just kind of stop after a little bit. And so we have some examples here in example 2, right, which I want to find the Maclaurin polynomials, or another way to say that would be the Taylor polynomials centered about 0. So again, that's just a little bit of vocab. of degree 5. So I don't want the infinite polynomial, but I want to stop after degree 5. Okay, so let's go ahead and give this one a go. The natural log of 1 minus 2x. Well, again, kind of going back up here, I see that the natural log is listed on our formula sheet. And so I have natural log of 1 plus x. So let me go ahead and write down maybe the natural log of 1 plus u is equal to, and copying from above, this is the sum from n equals 1 to infinity, negative 1 to the n minus first power times x to the n divided by n. And again, remember I'm using u, so I guess I shouldn't use x there. It should be a u. And we're going to go ahead and do some substitution. So let's see, u should be equal to negative 2x. So I'm going to go ahead and substitute that in instead. And so I would have summing up from n equals 1 to infinity of negative 1 to the n minus 1 times negative 2x raised to the nth power divided by n. Okay, so that's what that looks like. But remember, we only want the degree 5 Maclaurin polynomial. So degree 5, so let's go ahead and instead of going on forever, right, instead of summing these things up to infinity, let's go ahead and just stop after a little bit. So I'm going to say this isn't really equals, but it's approximately the same as, and now we're just going to start. We're going to plug in 1, we're going to plug in 2, right? All that sort of stuff. We start at 1 because that's what it tells us to. So if I plug in n equals 1, well, let's see, I'd have negative 1 raised to the 0th power. We'd have negative 2x raised to the first power, and we divide by 1. So that's me plugging in 1 everywhere I see an n. So next up, let's go ahead and plug in 2. So that's going to be negative 1 raised to the first power. We're going to have negative 2x. We're going to square that, and we're going to divide that by 2. Next up, 3 and 4 and 5, right? You kind of get the deal here. So negative 1, this is going to be squared now. Negative 2x being cubed divided by 3. Ooh, and I do have enough room. How nice. A little bit worried. All right, now let's go ahead and simplify this, right? Really, this would be like plus dot, dot, dot. It would keep on going here. But okay, let's go ahead and simplify this down a little bit. When I take negative 1 and I raise it to the 0th power, I just get 1. Of course, dividing by 1 doesn't do a whole lot, so this is just going to be negative 2x. Raised to the first power, well, that's just negative 2x. All right, here we have a negative sign, so I'm going to make this minus. And let's see, we're dividing by 2, right? Dividing by 2. And then I have negative 2x, and it's all being squared. So when I square my negative 2, I'm going to get 4. And when I square x, I'm going to get x squared. So notice that we can actually cancel things out a little bit here. And the 4 and the 1/2 are just going to make 2. So, okay. Next up, we have negative 1 being squared. So that's going to be positive. I have a 1/3. And then I'm going to take my negative 2 and cube it. So that's going to be negative 8. And I'm going to take my x and cube it. So that's going to be x cubed. So let's go ahead and simplify things down a little bit. I'll move that negative sign out there. And let's just make this 8/3. So 8/3. Okay. Next up, let's see. We have negative 1 cubed is going to be negative 1. I have a 1/4, and when I take negative 2 and I raise it to the 4th power, that's going to be 16. And when I take x and I raise it to the 4th power, that's just going to be x to the 4th. And so again, we can simplify down. 16 divided by 4 is just going to be 4. And last one, remember, we're going for a degree 5 polynomial, right? So you can see that I have my 1st degree, 2nd degree, 3rd degree, 4th degree. And so I need to just get up to my 5th degree, and then we can stop. So let's see, when I take negative 1 and I raise it to the 4th power, we're going to get a positive. We have the 1/5. And when I take my negative 2 and I raise it to the 5th power, well, this is getting kind of annoying, but it's going to be negative 32, and then x to the 5th power. And so again, we can kind of go ahead and rearrange this a little bit and just simplify down, bring the negative out here, and that was 32/5. So this right here is going to be my answer, my Maclaurin polynomial, centered at 0. So notice that we just have x's raised to various powers. So that's why it's centered at 0, of degree 5. Okay, last one for this page, last little example here, 3 to the x. This one's kind of clever here. So I invite you, if again, this one takes a little bit of a trick, but maybe you pause the video, try to figure out what that trick is on your own, and then we can go ahead and spoil the surprise together. All right, so the trick is, right, looking at this list, again, we're trying to use this list of stuff in order to come up with these other nice Maclaurin polynomials and Maclaurin series. But in this case, right, we don't have e to the x. The best thing, or the closest thing that we have, is e to the x. Sorry, I said we don't have 3 to the x, I think. I don't know, it's all kind of blending together. But yeah, we don't have 3 to the x, but we do have e to the x. So I'd like to maybe induce a little complication here for good reason, right? I'm going to say that e to the natural log of 3 should be equal to 3, right? So, therefore, 3 to the x, that's going to be the same thing as e to the natural log of 3 raised to the x power. And of course, when you take powers and you raise them to even more powers, they multiply together. So I'm just going to write this as e to the x times natural log of 3. And so now imagine if I took this and I made this maybe like a u or something like this. Then we could go ahead and instead of e to the u, which remember according to our rule up there, which is summing up from n equals 0 to infinity, of now u to the n divided by n factorial, we could just go ahead and substitute in x times the natural log of 3. So e to the x times the natural log of 3, well, that's going to be summing up from n equals 0 to infinity, and we're going to have x times the natural log of 3 raised to the nth power divided by n factorial. And now we can just start expanding this out. So notice that this one starts at n equals 0. You have to be careful here. So starting off at n equals 0, I would have, let's see, x plus, x times the natural log of 3 raised to the 0th power divided by 0 factorial. X times the natural log of 3 to the first power divided by 1 factorial. So on and so forth. And again, remember we want a 5th degree Maclaurin polynomial. So we're going to keep on going until we have an x to the 5th power. So this is going to have an x to the 4th power. And then finally, we're going to have an x to the 5th power. And again, these aren't really equal because I stopped after a bit. So we'll just say it's approximately equal to this. Right? All right, and so this is probably a fine place to end. If you'd like to, right, we can go ahead. I'm running out of room here, unfortunately. I'll cheat using technology just a little bit so that way it all fits on this page. I'll do one line of simplification. Anything raised to the 0th power is just 1. 0 factorial, this is the weird one. Remember, 0 factorial is equal to 1 as well. So this is just 1 divided by 1, or we could just write it as 1. Okay, things raised to the 1st power. Well, that's rather boring here. It's just going to be itself, x times the natural log of 3, and 1 factorial, also 1. All right, squaring things now. So natural log of 3 being squared. 2 factorial is just 2. And of course, we have x squared. So again, trying to combine together all of my coefficients and all of my powers of x. Here we're going to have, well, the natural log of 3 being cubed. 3 factorial, so 3 times 2 times 1, that's going to be 6. And we have x cubed. Now we have the natural log of 3 raised to the 4th power, divided by 4 factorial. So 4 times 3 times 2 times 1, that's going to be 24. And then finally, we have natural log of 3 raised to the 5th power, x to the 5th power, and we're dividing by 5 factorial. So 5 times 4 times 3 times 2 times 1. You can get out a calculator something just to verify that that's going to be 120. Oops, that's my eraser. I meant to have the highlighter out. There we go. All right. And so I think, again, we've actually accomplished quite a lot here, a good approximation for 3 to the x, but I'd like to show you kind of what we've done, and I'm going to pull this up in Desmos, and so we can see that actually our answer here is actually doing something quite wonderful, that it's approximating 3 to the x quite well, actually. So let's go ahead and switch over to Desmos, and we can see what we accomplished. So here we are in Desmos. Notice that I have in the red, and let me just go ahead and hide this one for a second, we have the function 3 to the x. And then I have here summing up from 0 to n, and we're going to define that here in just a second, of our series that we came up with. So x times the natural log of 3 raised to the nth power divided by n factorial. So if I go ahead and I graph this, notice that I'm just summing up right now 0 to 1, right? Because I have my capital N is equal to 1. So right now I'm not doing a whole lot, and notice that it kind of barely resembles 3 to the x. I mean, at least it's good around 1, right? If I zoomed really far in here, for instance, we could say, yeah, you're doing pretty good right around 1, but that's about it, right? Kind of as you zoom out, you kind of see, okay, you're not really doing all that great of a job, right? This blue line is not really the same thing as this red curve. So let's go ahead and add, right? Instead of just going from 0 to 1, let's go from 0 to, oops, sorry, I meant to have steps of 1. That's my bad. So let's go ahead and add on another term. So this is now adding on this x times the natural log of 3 squared divided by 2 factorial. You can see it gets a little bit better. And we can keep on going. So we could add on the cubic term and the 4th degree term. And here is the 5th degree term. So this is where we stopped, right? We have a 5th degree Taylor polynomial right now. And you can see that it's actually doing a pretty decent job of approximating 3 to the x, at least on the window that I have here. Of course, if we zoom out, you'll see that it's not doing a perfect job. It seems to be doing a little bit better on the right-hand side than it is on the left-hand side. But you can also see that kind of if you increase this a bunch, oops, going up to 10, it starts to do even better. And we could even cheat a little bit and add an extra 0 here, right? So if I went to the 100th term, oops, added an extra equal sign for whatever reason. There we go. And now you can see that actually this blue line is completely covering this red one. And again, it's not going to be perfect. If I zoom out far enough, we could find out that they are going to be different from each other. But this is, doing quite a good job. Even if I zoom out to around, the tens, right? So negative 30 to 50 or so, it's still doing pretty good. It's only, let's see, where does it actually differ? Oh, there we go. It starts going crazy over here. So yeah, adding together all these values, it's starting to have a really hard time around negative 30 or so, apparently. But up until then, it's actually doing pretty good. All right, so that is what we've accomplished. That's what these Maclaurin or Taylor polynomials are doing. They're being used to approximate other functions. Okay, so that is the first step. That's the first type of problem, I think, and this is the nicest case. Making things a little bit more difficult, we will have some that unfortunately, right, that these rules do not help us with. So there are some that these rules here that we have on our formula sheet, they just don't help us with. And so we need the Maclaurin series general definition, right? So this is also on our formula sheet as well. The expanded view one isn't so much, but kind of this bit over here where you actually have this sigma notation, that one's on there. And so here's an example problem in which kind of as you go back and you look at all the things that are on our formula sheet, right, none of them can really replicate a square root of x plus 4. So we go down this list, sadly, nothing really works. And so sadly, this list doesn't help us when it comes to trying to recreate the square root of x plus 4 in its infinite polynomial form, aka its Maclaurin series or Taylor series. So we would like to still come up with it. We're going to find the 3rd degree Taylor polynomial. This is sometimes denoted with t sub 3. You'll see this a lot on web work. And we want to center about the point x equals 0. And so the big thing here is let's go ahead and use our definition for this. So again, what we have in this box right here. And notice that we need lots of derivatives, right? We need actually, so the function's value at 0, we need its derivative at 0, its second derivative at 0, and its third derivative at 0. And then again, it would go on forever, being an infinite polynomial and everything, but we only want the third degree. So we're going to stop after that. So let's go ahead and take a little bit of time. I want to calculate out f of 0, f prime of 0, the second derivative at 0, and the third derivative at 0. So that's going to be the first order of business. Well, here's our function over here. And so the first thing we could do is plug in 0. So the function's value at 0 is just going to be root 4, or that's going to be the same thing as 2. So that one's really not so bad. Now we need to start taking derivatives. So maybe I should do, maybe first up, let's figure out what the derivative is for our function, and then we can plug in 0 to it. So, well, remember the square root is the same thing as being raised to the 1/2 power. So let's go ahead and when we take the derivative, right, that 1/2 is going to come down. We're going to reduce our power by 1. So that's going to go to negative 1/2. And then I'd multiply by the derivative of the inside. Well, the derivative of the inside is just going to be 1. So it's really not all that exciting. So now that we have the derivative, though, we can plug in 0. So when I plug in 0 here, I'm going to have 1/2. And then I'm going to have 4 to the negative 1/2 power. And let's go ahead and spend a little bit of time now and simplify this. Remember, whenever you have a negative exponent, that's the same thing as division, right? So we're taking the reciprocal of this. And so this is just going to be 1/2 times 1/4 to the 1/2 power. And remember, raising things to the 1/2 power, that's the same thing as the square root. So the square root of 4 is going to be 2. So 1/2 times 1/2, that's going to be 1/4. Okay, let's go ahead and try another one here. We need the second derivative. So second derivative, so that's just going to be the derivative of this. So we take the derivative, the negative 1/2 comes down. Combining with the 1/2 that's already there, we get negative 1/4. And we reduce our power by 1. So I'm going to have negative 3/2 now. And now we can go ahead and plug in 0 everywhere I see an x. So I'm going to have negative 1/4, and I'm going to have 4 raised to the negative 3/2 power. So again, let's go ahead and take a line or so to simplify here. So the negative 1/4 is just hanging out there. And then again, we have some division. So this is going to be 1 divided by 4 raised to the 3/2 power. Again, the 1/2 power is just taking the square root. So I could go ahead and take the square root of 4, and I'd get 2. But remember, now there's that 3 there as well. So you also have to cube it. So when you cube 2, you're going to get 8. So this ends up being negative 1/32. So remember, whenever you have complicated rational exponents, right, you're allowed to kind of break them up and do them one piece at a time. You're allowed to do the 1/2, aka the square root, and then you're allowed to cube it. And really, you can do the order in either way. So you can do the cubing first if you really wanted to. That also works out fine. All right, last one. Bring the negative 3/2 down. We're going to have 3/8. Reduce our power by 1. Multiply by the derivative of the inside, which just happens to be 1. Now we plug in 0. So we have 3/8. We have 4 raised to the negative 5/2. And so, again, this is going to be division. The negative exponent there, so 4 raised to the 5/2. And when we take something, we raise it to the 1/2 power, we're just going to take the square root. So the square root of 4 is 2. And when we take 2 and we raise it to the 5th power, that's going to give us 32. All right, so let's see, 32 times 8. Is that like the 256 or something? So 240, yeah, 256. Cool. All right, so now we have all of the pieces that we need. Now we need to go ahead and kind of just assemble them. So notice using this formula up here, and we're just doing the third degree Taylor polynomial. So if you wanted to, you could call this T3. We're going to have our f sub 0, so that's 2, plus f prime of 0, so that's 1/4 from what we have calculated up here, times x, plus the second derivative, so that was negative 1/32. So let's go ahead, negative 1/32. And let's see, we need to have x squared, and we need to divide that by 2 factorial. So 2 factorial is the same thing as 2. And finally, the third degree bit, so our third derivative, So 3 divided by 256 times x cubed, and we divide that by 3 factorial. So 3 times 2 times 1, that's going to be 6 here. So of course we can combine, simplify a little bit. So 32 times 2, that's going to be 64. And there's all of our coefficient stuff, and then the x's can just be over here by themselves. That's nice. And then here we're going to get a little bit of cancellation. So the 3's would cancel out, and we'd have an extra 2. So 2 times 256 is going to be 512. So we could go ahead and make this a nice 512. And everything canceled on top. And so this is just going to be 1 over 512 x cubed. So this right here would be the Taylor polynomial of degree 3. And if we wanted more terms, that's fine, right? It could ask for a 4th degree or a 5th degree or anything like this, and then we would just keep going, right? You can see from this trend here, next up would be the 4th derivative at 0 divided by 4 factorial times x to the 4th. And we could do this as many times as we wanted, right? Summing up kind of each one of these as we go. All right, so I haven't given you guys a whole lot of time to work on your own, but here's one where I think it would be a good idea to pause the video, give this one a go, and we'd like to find the power series representation in sigma notation, right, for the sinh function, right? So hyperbolic sine about x equals 0. And so please pause, try to use this definition up here, and come up with a power series representation in sigma notation for sinh. All right, so this is how far I've made it so far. I've taken derivatives of hyperbolic sine, and I've plugged in 0, right? Because it says that we're centered about x equals 0. So I've done all this. I got 0, 1, 0, 1, rather boring, right? And then I went ahead and I plugged it in for our definition. For, again, we're looking for the power series representation, or the Taylor series, centered about 0 for sinh. And we can see that we got the 0, 1, 0, 1. So it seems to be taking off all of these even bits, right? So this one is 0, this one's 0. And so we just have all of the odd ones, right? And kind of as we imagine this continuing, it would just go 0, 1, 0, 1 forever sort of deal. And so this actually reminds me of one of these, right, that we had back in our video notes, and maybe it's a little bit harder to see it in its expanded form just by looking here at sigma notation, right? But the sine right here, sine has the same thing where it only has odds, right? 2n plus 1 divided by 2n factorial. But the big thing here is that it's alternating. So again, if I pop back over to our video notes, this is where we also have it in kind of the expanded form, right? You see for sine, it goes x divided by 1 factorial minus x cubed divided by 3 factorial plus x fifth divided by 5 factorial. And that is essentially what I want here. Oops, clicked the wrong one. That's essentially what I want here for our problem, except for I want all of them to be positives, right? It doesn't seem to alternate back and forth between positive and negative. And so the correct answer for this one in sigma notation is going to be summing up from n equals 0 to infinity. And again, I'm basically copying down what I had for sine, which again, maybe isn't all that surprising because this is hyperbolic sine after all. And I'm going to have x to the 2n plus 1, so all of the odds, divided by 2n plus 1 factorial. So again, kind of we see these factorials down here that seem to correspond with whatever degree x is. But then we leave them all positive. So we don't have this alternating piece, plus 1, minus 1, plus 1, minus 1, right? We just keep them all positive. So this right here is the correct power series representation, or Taylor series representation in sigma notation for hyperbolic sine, centered about 0. Okay. And so that's kind of these level 2 style problems, I would say, where kind of they don't exactly fit what we have here in this box. We have to go back to the definitions for Maclaurin polynomials and Maclaurin series. The last thing, I would say the level 3 problems, right, kind of come from things that are not Maclaurin series whatsoever. So remember that great and wonderful box of all of this information only works for Maclaurin. So, right, if this is not a Maclaurin series, then these common power series that we're given are useless. We need to use the Taylor series definition. So I've seen a lot of points taken off as well for making this mistake. And so actually for example 5 that we're going to be doing, right, we already did x e to the x in Maclaurin series, but here we're going to be centering it about a equals 1, just so I can really emphasize to you how different these series end up being and how much work actually, more work this one is over the original one where we just had to do x times and then this common power series of e to the x. So again, here's my kind of truncated definition. So I just have if f is nice. So again, kind of this is going back from the video notes, that the formal definitions there, but this is, the highlights. So we're centering about x equals a in this case. Then our function f of x is going to be the same thing. And again, instead of plugging in 0, we're just plugging in a, right? So f double prime at 0, the third derivative at 0, so on and so forth. And notice we're centering about a. So you see x minus a squared, x minus a cubed. Again, kind of going back from our power series stuff in 11.8, but now with a different center. And kind of the most generic form, or kind of in the sigma notation form, we have something like this. So again, this is directly from the video notes. Okay, so let's go ahead and try to apply this. And again, there is no other way to do this problem right here because we're centering it about a equals 1. So we can't use that wonderful table of well-known power series or well-known Maclaurin series for e to the x. So let's go ahead and get to it. Remember, in this case, we want the full Taylor series, so not just a Taylor polynomial. And I find that the most difficult thing about coming up with a Taylor series like this is, again, trying to figure out what is the nth derivative. What is a formula for the nth derivative for our function at a? So in this case, at 1. So usually in order to do this, I do a bit of a running start, right? So I want to figure out what is the function's value at 1. What is the first derivative of the function at 1? What's the second derivative of the function at 1? And maybe by then I have enough information that I can go ahead and guess what the formula would look like. What is the nth derivative of f at 1? So, okay, let's go ahead. Here's our function up here. Let's plug in 1. So when I plug in 1, I'm going to get 1 times e to the 1. So that's just going to be e. Okay, not so bad. Let's go ahead and take a derivative, right? So f prime of x. Well, notice that in this case, I have to go ahead and use my product rule. So the derivative of the first times the second plus the first times the derivative of the second. I get something like this. And when I plug in 1 into this, right, I'm going to have, let's see, e. So 1 times e to the 1 plus 1 times e to the 1. So it's just going to be e plus e, or that's going to be the same thing. Let me write it as 2 e's. Okay, let's take yet another derivative. So, okay, the derivative of e to the x is going to be e to the x. And the derivative of x e to the x, again, I need to use the product rule. So I do the derivative of the first times the second plus the first times the derivative of the second. Okay, and now we need to go ahead and plug in 1. So I plug in 1, I get e to the 1, e to the 1, 1 e to the 1. So I get e, all being added together. So that's going to be 3 e's. So notice, when I took 0 derivatives, I had 1 e. When I took 1 derivative, I had 2 e's. When I took 2 derivatives, I had 3 e's. It always seems that the number of e's that I have is 1 more than the number of derivatives I'm taking. And so if I'm taking n derivatives, I would conjecture that we should have n plus 1 e's. And so this right here is going to be the general formula for the nth derivative of f at 1. Again, that's the hardest bit. Now we can go ahead and use our definition. So f of x is going to be equal to summing up from n equals 0 to infinity. And it goes the nth derivative of f at a. So in this case, at 1. So that's going to be my n plus 1 times e. We divide it by n factorial. Again, we're just kind of following this definition back here. So this is what I'm thinking about or looking at. So I've divided by n factorial, and then I need my x minus a raised to the nth power. So x minus a, again, remember my center was 1 in this case, raised to the nth power. So that right there would be my final answer as far as what is the Taylor series for our function centered about 1. We could then use this series in order to figure out its radius of convergence. So that's the second part here. So this one I'm going to have to use the ratio test on in order to come up with it. So if we use the ratio test, we're going to have the limit as n goes to infinity, the absolute value, this would be n plus 2 e's divided by n plus 1 factorial times, let's put this in the numerator here, I suppose, x minus 1 raised to the n plus first power. So that's my a sub n plus 1. And now we're going to divide by a sub n, or I'm going to multiply by the reciprocal. So I'm going to have n factorial on top. I'm going to have n plus 1 e's on bottom, along with x minus 1 to the nth power on bottom. And so again, a lot's going to be canceling here. So for instance, this e's, they just perfectly cancel. We get quite a lot of canceling of these x minus 1s. So there's n plus 1 of them on top and n of them on bottom. And so let's go ahead and clean this up a little bit and just see what we have. So the limit as n goes to infinity, and I'm going to combine the like pieces that are left over here. So I'm going to have n plus 2 and n plus 1. Let's see, the e's canceled. A lot of the x's canceled, so I have x minus 1 left over here on top. And then I have n factorial divided by n plus 1 factorial. And so remember how these factorials kind of cancel. If we were to start expanding this out and writing these things, n factorial looks like n times n minus 1 times n minus 2 times all the way down to 3, 2, 1. And n plus 1 factorial would look like n plus 1 times 1 lower, n times 1 lower times all the way down to 3, 2, 1. And so again, there's going to be a lot of canceling that happens. The n's cancel, the n minus 1s cancel. Everything essentially cancels, except for, on the bottom here, we have an n plus 1 left over. And so we're going to be left with the limit as n goes to infinity, n plus 2 over n plus 1. Notice these absolute values really aren't doing anything. All of this stuff is positive for the n's anyway. We would need to apply them to our x's. That's fine. And then here I'm going to have 1 divided by n plus 1. So as n goes to infinity, this is going to be 1. This doesn't have any n's, so it's just is what it is. And this is going to be 1 over infinity, right? And of course, when you divide by a larger and larger value, right, this is just going to be 0. So we're going to have 0, and the question is 1 is 0 less than 1? Well, it's always less than 1, right? No matter what x value you choose. And so the radius of convergence is going to be infinity. And so, okay. We did end up getting the same radius of convergence as we did for our regular old e to the x that we had on our sheet. But notice, right, so down here I say compare this answer with example 1a. Right, so example 1a, way back up here, notice we created this function x e to the x, but we were centered about 0, right? We were trying to find the Maclaurin series. And so in this case, we just had 1 over n factorial, x to the n plus 1. And that's all there was to it. We also had a radius of convergence of infinity, but now look at how much different we have, this answer is. And all of the work that required, right? Before we just multiplied something by x, essentially. But here, kind of, we had to figure out this general formula for the nth derivative. Again, our result doesn't really look anything like the original one from 1a sort of deal. And so that's the big thing that I wanted to point out here, is that when you have a different center, centered about a equals 1 in this case, instead of a equals 0, right, it alters your results quite a lot. You can't just use the thing centered at 0 to come up with this Taylor series, unfortunately. So make sure if you see a problem like this that you use this, you go back to this definition, right? This is the only way to really come up with this. Okay, so I have one more for you. And again, I think it'd be a good idea for you to pause the video and try this one out on your own, and then we can come back and spoil the surprise together. So again, please try this one out on your own, and then we'll see the results. All right, let's talk through these results together. So again, I need to come up with, usually the most complicated thing here is coming up what does the nth derivative of f actually look like. And so here I have some work in order to try to come up with that. Of course, plugging in 2 isn't hard. I can plug in 2 into the natural log. I just get the natural log of 2. And then we go ahead and we start taking derivatives. So the derivative of the natural log is going to be 1 over x. The second derivative is going to be negative 1 over x squared. So again, kind of the negative 1 comes down. I reduce my power by 1. Next up, I have take another derivative. And notice I try to leave this in the unsimplified form whenever possible. And so I have negative 1 times negative 2 divided by x cubed. And then after that, negative 1 times negative 2 times negative 3 over x to the 4th power. And after that, I think maybe I can start to see what the trend is more or less. I've went ahead and I've started to plug in 2's over here. So I have 1 over 2, negative 1 over 2 squared, negative 1 times negative 2 over 2 cubed, and negative 1 times negative 2 times negative 3 over 2 to the 4th power. And so we can see maybe when I'm taking my 4 derivatives here, so when I'm taking 4 derivatives, I do have a 2 to the 4th power. I seem to have something that's kind of like a factorial, right? So I have 3 times 2 times 1. It starts at 3, so it's 1 lower than the number of derivatives that I took. And then there's this whole alternating piece, right? So in this case, the 3 negatives together would make, kind of like this negative 1 raised to the 3rd power. This would be the negative 1 raised to the 2nd power. This would be negative 1 raised to the 1st power, right? So these alternating number of negative signs, this is kind of this negative 1 piece. So here's what I've come up with for what I believe my nth derivative for my function at 2 would be. So again, I have this alternating piece. I have a factorial, but with 1 less than the number of derivatives that I'm taking. And I have the same number of 2's that I have derivatives. So 2 to the 4th power, for instance, was the one that I looked at back here. And 2 to the 3rd came before it, 2 squared. So this is what my nth derivative of f is at 2. And notice this works essentially, except for this first one. This first one's a bit of a problem, right? It's just the natural log of 2, and that's the only one that really doesn't fit the form, and so I'm just gonna take it off to the side here and forget about that to some extent. So notice I've just written for n is greater than or equal to 1. And so when I've gone and I've written out my Taylor series for this in sigma notation, I just have natural log of 2, so the 0th term here. So when n equals 0, it would just be the natural log of 2. And then starting at n equals 1 and going on, then we actually have a pattern. So notice that we have my nth derivative of f at 2. That's all this bit. I've divided by n factorial. And we've multiplied by x minus a to the nth power. So that's this bit here. So now I've just assembled it using that formula that we were given on the last page. Of course, we can simplify things a little bit. Notice that we have some factorials here, n minus 1 factorial, n factorial, and so those will cancel out and you can be left just with n, for instance, so a lot of things cancel. And so this is kind of as simple as I could possibly get the answer right here. If you use the ratio test, you can see that actually your radius of convergence is going to be 2 in this case. So you can verify that. Okay, well, this has ended up being a bit of a long video, but that's good. I hope that you've taken a lot from it. If you have any questions, please post them on Piazza, or please visit me in my office hours. I haven't had that big of a turnout yet for office hours, so I'm really hoping that that catches on and that you guys utilize this well and everything. But yeah, make sure if anything was confusing, please reach out. I'd be happy to talk to you about this more. I hope you guys have a wonderful, well, right now it's Friday, so I'm thinking about the weekend. Hope that you have a wonderful weekend. If you're watching this on Monday or Wednesday or whatnot, I hope you have a wonderful rest of your week. Otherwise, I will see you guys next time. We'll talk a little bit more in detail about, again, continuing 11.10 and 11.11. We're going to be using these Taylor and Maclaurin series polynomials to actually do things. So right now, we've been just calculating them. Next up, what are they good for, right? What are they going to be used for? That's next. All right, I'll see you then.